Hi everyone, this is João again, and this is the first video of PA8, so exercise 5.1. So in this exercise, we have a fabrication process with a minimum length of 0.18 micrometers, an oxide thickness of 4 nanometers, okay, and we have a mobility of the electrons at the surface of the channel that is 450 square centimeter per volt here. So those two here I've covered. We have a threshold voltage of 1 volt, and notice that we are using small t now to not confuse you with the thermal voltage. Remember from the BJT we were using VT, so capital V capital T as 25 millivolts, so now it's the threshold voltage. And we also know that the oxide permittivity is 34.5 picofarad per meter. Okay, and in part A we need to calculate the process transconductance. So the process transconductance Kn prime is equals to the mobility of the electrons times the oxide capacitance. And the oxide capacitance, okay, so this term here, is calculated using the permittivity per meter of the oxide divided by the thickness of the oxide. This gives us 34.5 picofarad per meter divided by 4 nanometer. So this pico here is 10 to the minus 12, this one here is 10 to the minus 9, and the result is 8.625 times 10 to the minus 3 farad per square meter. Okay, so that's the first number that we have to calculate in part A. So now that we have the oxide capacitance, we can calculate the process transconductance, and this gives us a Kn prime equals to those 450 square centimeter per volt second, and we need to convert that to square meter per volt second, so we multiply by 1 meter, 1 square meter divided by 10k square centimeter, right? So this one here cancels with this one, and times those 8.625 10 to the minus 3 farad per square meter. So the process transconductance is equals to 388.125 microampere per square voltage. Okay, now on part B we still have the same parameters for the process, the fabrication process. This is the minimum length, right? The oxide we use and the mobility we use to calculate the process transconductance. But now we need to figure out what's the value of W to get this resistance here. If we have the minimum length for the length of the channel and a VGS of 1.0 volts, okay? So if we want to calculate the width of the transistor, okay, first we know that the resistance between drain and source is equals to 1 divided by the process transconductance times the aspect ratio, which is W divided by L, times the overdrive voltage. Now this length here we know that is the minimum length of the process, so 0.18 micrometers, and this one here we still need to define, right? So first, if we rearrange this equation here to get W in the left hand side, we can rewrite as W equals to this L here goes to the numerator, so it's L, and I write L minimum because that's imposed by the problem, divided by the process transconductance times the drain source resistance times the overdrive voltage. Now the overdrive voltage is equals to the gate source voltage minus the threshold voltage. This gives us 1 minus 0.5, that's 0.5 volts. So if we substitute those values in the equation for the width, we get 0.18 micrometers divided by 388.125 microampere per volt squared volts times the resistance, so 1k ohm, times the overdrive voltage 0.5. This gives us a transistor width of 927.6 nanometers. That's roughly 0.93 micrometers. So if we have the transistor with the minimum length, that is 0.18 micrometers, and we manufacture, we build this transistor with a width of 0.93 micrometers, and we insert this VGS here of 1 volt, right, and considering that the threshold voltage is 0.5, we get this resistance of 1K.